Hello. Last video I told you that I probably wouldn't be doing any more videos when commenting on Brian Mullin's work. Now, first of all, I would like to, that is obviously not true because I'm doing this video, but first of all I would like to state something that I mean seriously and I want people to consider and respect on my channel. I have no reason to doubt that Brian Mullin is a smart guy. I have no reason to believe that he's stupid, and I have absolutely no reason to believe that he isn't an engineer, as he claims to be. No reason at all. I'm not making these videos to put Brian Mullin down, to somehow make him look dumb, or to disrespect him. I'm doing this to having some sort of dialogue, a weird kind of dialogue, more like a battle where I say something and then he says something and then I say something. It's not a real dialogue, a live dialogue, but it's more like letters forward and backwards. So that I want to be absolutely clear about that. That's what I think and that is what I mean. I don't want anybody on my channel saying, well, Brian is just so dumb, how can he not be an engineer, how can he be an engineer, he must have a stupid boss, something like that. I don't doubt that Brian is a great guy and a smart guy, none whatsoever, alright? And this ping pong backwards and forward, I would actually like to have a dialogue with him, not direct dialogue because I'm horrible on Skype or something like that, but this kind of dialogue would also work for me. Alright, so in this video I will address his explanation about conservation of momentum, where I think he makes a crucial mistake. But first I would like to say that he is actually giving me a quite good idea. That instead of you seeing me writing something on the board, on the whiteboard, and that takes time and time, then I'll just stop the video and then cut and edit, so when the video starts again, you'll just see me with the new drawing. Now I will be doing some small calculations, but the big ones I will just put on the board and then explain what's going on. Alright, so the first thing is that on one of his videos he's asking about, well, if a satellite or the space station can radiate energy outwards into space, then why doesn't the same happen on Earth? And I would like to say that that's actually an extremely valid question. Why doesn't that happen? So he makes this drawing. I'm just sketching it. It's not exactly what he made, but it's something like that. He had the ISS blown out and something like that. Yeah. So this is we have the sun out here, and these are the light rays. So it just says, well, the light rays hit the Earth, warm it up, but the Earth radiates heat or energy outwards into space again. That is correct. So why isn't it blatantly cold on this, really freezing cold, death freezing cold, on this side of Earth, and then when we come up here where the sun is, it should be extremely hot, right? Now, the answer for this question is atmosphere, and that is also the reason why some planets, or especially asteroids, the moon for example, have so incredible temperature differences between the night side and the day side. That is because there's no atmosphere around it to regulate this temperature. Now I'll try to sketch quickly on the whiteboard how sort of conceptual idea of how the energy transfer on the Earth goes on. And of course, like I said, I will pause the video, draw it, and then talk about it. Alright, so now I've drawn the new drawing I want to show you, and I will try to sort of explain the conceptual idea about why the Earth doesn't get instantly cooled down on the dark side of the Earth. And well, in general, this is also the basic idea of how you would make a global climate model. So what goes on here? Well, first of all we have, maybe I should put in here that clouds are also made of water, H2O. But in general, we have the sun out here. The sun. And in comes, this is sort of a simplified example, in come three rays. This is invisible light, I would like to state. So the first ray here hits the Earth, and when the visible light ray hits the Earth, it is transferred to thermal energy. There's a transfer difference between when the energy of the ray hits the ground and the transfer energy, but out comes an infrared or thermal radiation. This now water can reflect thermal radiation or infrared radiation, so can carbon dioxide, methane, and water, as I said. What we all call these gases. Sorry, I just had to look up the word. I couldn't remember it. They are called greenhouse gases. Now, water is not specifically a greenhouse gas, but it contributes anyway. So, at first, this visible light ray hits the ground, and then is converted, or transfer energy, how you want to say it, into an infrared or thermal radiation light ray. Then it hits a cloud in the sky, and because the cloud is water, it is reflected back towards the Earth. Then we have another ray. It comes here, hits the ground, is converted into an infrared, again thermal radiation, but escapes out into space because it is not reflected by anything. It doesn't hit anything. And then finally we have the third ray here, also hit the ground, converted into thermal radiation, escapes the cloud cover because it doesn't hit a cloud, but then hits something up here. It could be carbon dioxide, it could be a methane molecule, could be a water molecule, probably not water, but anyway, sorry. Some of these greenhouse gases hit some kind of greenhouse gas, and then it's reflected back toward the Earth. Now, if we removed all of this, the cloud, carbon dioxide, methane, all we have here, basically removed the atmosphere of the Earth, then this would escape out. All the heat, all the radiation coming from the sun, hitting the ground, converted into thermal radiation, would escape outwards again. And even the thermal radiation coming from the sun, because even though the sun's main contribution, the main radiation from the sun is in the visible light, that's where the most energy is, then there's also both infrared and ultraviolet radiation and further out. First of all, without the atmosphere, we would be instantly radiated hard by ultraviolet radiation, which would kill us basically. We would also be hit by microwave radiation, all sorts of bad things that's reflected by our atmosphere. But the infrared radiation would hit the Earth, warm it up, right? But the Earth would radiate that outwards again. So in that case, without an atmosphere, Brian Mullin is correct. But we have an atmosphere around the Earth, and that is what keeps our Earth warm, in a reasonable good warmth, and it's also why the warmth is kept inside the environment of the Earth. Some escape, but it's like having something, you could call it an insulating matter, insulating the Earth. Yeah. Alright, so now I'm ready to look over Brian Mullin's conservation of momentum example. Now, in this case, he used hose. When you hold a fire hose, then you turn off the water sprays out, and then you feel a jog in the opposite direction as the water is spraying out. This is exemplified in his terms, and also in mine, by using, you can use action-reaction. So I have rewritten the values. He used an R for a reaction, but basically what I have done is to say that my positive x direction is that way. So anything going that way is positive, anything going this way is negative. So since the force of the hose, the reaction or the force on the hose is negative because it goes in that direction, and the water is going in that direction, the force of the water is going in that direction. The velocity of the water is also in that direction. But in any case, then the force of the water is positive. So I've written it here. The force of the water is equal to the negative or the reaction of the force of the hose. Alright? Now, he did sort of a little work of how to derive the conservation of momentum equation, and I don't disagree with that, so it would be foolish for me to spend time on deriving something that is the same that he derived. We agree on that. And we also agree that when you, depending on which direction you say is the positive and negative and how you do it, then that the negative, in my opinion, the negative mass, then the negative, you could also write it this way. The negative momentum on the hose is equal to the momentum of the water, or if you want to write it in a different way, that that if you take the momentum of the water and subtract from the momentum of the hose, then you get 0, that is, momentum is conserved. Now, that is, since the momentum is m times delta v or something, sometimes you just write mv, but in it that's basically saying the same. When dealing with this hose, we have the water coming out in that direction, having it's basically not important, but depending on where you want to set your initial values and where you want to set your initial velocities, we have that the initial velocity of the hose is when the water is in here. That's the baseline, and then as it goes through here, the nozzle gets smaller, and that means, as correctly stated, that the exit point for the water is small, but you have to press the same amount of water through that hole, hence the velocity have to increase, and also from that the energy, because you have 1/2 mv squared is the kinetic energy. Alright? So in basic, we can say that the total velocity of the hose, or the velocity difference between these two, is the final velocity, that's here, minus the initial velocity, that's here. Now for the hose, which is initially at rest, we do the same. So we say, well, the velocity of the hose is also the final velocity of the hose minus the initial velocity of the hose. And that, since the initial velocity of the hose is 0, then we have the final velocity minus 0, and that is just the final velocity. So we can put that into our equation and move it around a bit, and then you will get that minus the final velocity of the hose, because it's moving in this direction, is equal to the mass of the water times the, in parentheses, the final velocity of the water minus the initial velocity of the water divided by the mass of the hose. This is basically also what Brian Mullin gets, and we agree on that. But then he introduced something that I don't agree with. He says, well, the basic way, the reason why you feel this jog or this push when you open the hose, open the water in the hose or let it go, is because the water is pressing against the air. There's something to push against, right? But that's not what he stated in his equation. That is definitely not what he stated in this equation. In this equation he has only the force between the water and the hose. If you want to include the air, then you should write something like this, right? Oh, sorry, this should be a plus. The force of the air plus the force of the water is equal to minus the force of the hose. But that doesn't work either, because then you have some sort of, then the air would do positive work on the hose. And that doesn't really work, right? You can alleviate this by saying, well, we have also the pressure of the air on the other side. But then you can just cross them out. Then you have the same equation, right? And if he's saying that the force of the water, the air is actually, not the water itself, but the air is reacting with the water through, it is the reaction of the hose and the air with the water as the medium. Then the equation should be not. Then the equation should be, let's see, if air, well, you can see that's negative, so we'll have to, but we'll have to say that the force of the air is equal to minus the force of the hose, right? I know that there's a problem here because that is basically what, but you can say that, well, you will have that the force of the water is equal to minus the force of the air, right? That's the reaction between the force of the air and the force of the water. And then we had before that the force of the water, well, we will actually get this, right? So that doesn't even make sense. So when Brian Mullin is analyzing this situation, which he does perfectly until he gets to talk about the reaction between the air and the water, is he has to look on which forces he's including in his equation. Now, if he's stating that the reaction giving you the pull, opening the hose, is a reaction between the air somehow, then the air have to be included in that equation somehow. You can't just write something like this. Say minus F hose is equal to F water. This equation here, minus F hose minus F hose is equal to F water. Then do some calculations and get this, and then this. And then they say, well, I'll also introduce the force of the air between, and then say that is the reason why we actually feel this, because it doesn't work that way. If the force of the air has an influence on the hose, then it has to be included in this equation somehow. That is how it works. Now, the final thing I want to say in this video is that, well, this is a lot of math. It's not complicated math, but there's a lot of math, and there's algebraic equation and moving things around. And someone said, well, if you could cut past the math bull. Brian Mullin also said it in one of his videos that Einstein had said, well, if you understand something fully, then you should be able to explain it to someone else. Said in other words, if you can't explain something in simple terms, then you haven't fully understood it. I can, to the most part, agree with that announcement. But the problem with this is that I would love to convey the conceptual ideas here. Just cut all the math away and then just give the conceptual ideas how things work. That would be totally the most easy for me, because I don't have to write a lot of equations and do a lot of derivations or anything like that. And it would probably also be easier for you, because you don't have to wrap your head around so many formulas and can these calculations be correct. But the problem arises when some of you says, I don't believe what you're saying, prove it. If you look past the obvious that I don't prove anything in science, and science and physics don't prove, we actually disprove. But if we set that aside, then the only way to prove anything in physics is to roll out the math and show you, well, if we calculate, if we account for the forces and do our calculations, then we get this. And then we can't just add another force into this system without also include in our calculation. It's simply wrong, right? So what would the conceptual idea, what is this here? Well, the conceptual idea is that when you spray out water from a hose, then that spraying out is giving an equal reaction in an action in the opposite direction of equal strength, which is what you feel when you do it. And it doesn't have to be a fire hose. It can be a simple garden hose. It could be a soft gun. It could be a gun. It could be a rifle. It could be anything. Throw a ball. But that's a little different because you don't actually feel it, but you can feel the inertia, the unwillingness of the ball to get moving, to change direction or to accelerate actually. But in general, that is the conceptual idea here. But if you want to see, can this really be true, then we have to roll out the math. Alright? I think that sums all about what I wanted to say in this video. Thank you for watching.